Hello students, in this video we'll discuss the catenoid and helicoid in proof. Let's recall, a parameterized surface is a minimal surface if its mean curvature h is equal to 0. And furthermore, if the metric on the surface is conformal, then the Laplacian of the parameterization is equal to twice the conformal factor, 2 e to the 2f times the scalar curvature. Not scalar curvature, but the mean curvature, right? Where here, the first fundamental form is e to the 2f du squared plus dv squared, like that. So if we have conformal metrics, then we know the Laplacian is equal to twice the conformal metric times the scalar curvature. Okay, great, that's awesome. And so let's do some examples of this, right? So the first example we're going to consider is a surface of revolution. This is called the catenoid. Okay, and so the catenoid is obtained by rotating the hyperbolic cosine function around the axis, right? So in other words, I can parameterize this by r of u and v is cos of u cosine v, cos of u sine v, and then just au. So in other words, I have a parameterization. I've just rotated the hyperbolic cosine around the z-axis here. So we get this sort of a shape like so. So this shape looks like this. This surface looks like this. Just hyperbolic cosine. And then that is just rotated, right? So this is a surface of revolution. So in other words, we have a shape like this. And the important thing to realize too is that this goes on forever, right? So this is not compact, right? So that's when I'm just gonna make this observation because in further videos, we're gonna understand properties of compactness relative to minimal surfaces, okay? And so let's find the first fundamental form of this thing, right? So what's Ru? So Ru for the catenoid is going to be a sinh u cosine v, sinh u sine v, and then a 1. What's my RV going to be? My RV is going to be a negative cos u sine v, and then a cos u cosine v, cos u cosine v, and then a 0 over here, right? So what is my first fundamental form? My first fundamental form 1 is going to be what? It's going to be ru dot ru. It's going to be sinh squared cosine squared, sin squared sine squared plus 1. Okay, that's great. So I'm going to have a 1 plus what? 1 plus sinh squared of u. That's my du term, du squared. Great. And then what's my RE to RV? Well, this is going to be 0. These two terms are going to have the same thing. They're going to have a sinh, a cos, a cosine, a sine, and they're opposite signs. So it's going to be 0, and that's nothing. So there's no cross term over here. And then finally plus what? And then finally plus cos squared, sine squared plus cos squared, cosine squared is cos squared of u dv squared. Now you might say, wait a minute, this isn't conformal. Well, actually it is, right? Because 1 plus sin squared is cos squared, right? So this is really just cos squared of u. And then what? And then du squared plus dv squared. So in fact, this is a conformal metric, right? Excellent. And so now, of course, the beautiful thing is let's compute the Laplacian of this thing. So what's RUU going to be? So RUU is going to be a sinh, we'll see a cos u cosine v, cos u sine v 0. And what's RVV going to be? RVV is going to be a, negative cos u cosine v, and then it's going to be a negative cos u sine v 0. And lo and behold, if I add these things together, what do we get? If we add these things together, this plus this is 0, and this plus this is 0. And we know, therefore, that RUU plus RVV on one hand is equal to 0. On the other hand, is equal to e to the what? E to the 2f, which is just a conformal factor over here. So it should be cos u, cos squared u, times H, and that forces, of course, H to be equal to 0, and that implies that this catenoid is, in fact, a minimal surface. We have an example of a minimal surface. In fact, later we'll see that this is, in fact, the catenoid is the only minimal surface revolution. So just remark, that's just involves solving a differential equation, right? So remark, catenoid is the only minimal surface revolution. Excellent. That's our first example of a minimal surface. Let's do the next example. Next example is a helicoid. The helicoid is defined as follows. That's R of u and v is sin u cosine v, sin u sine v, and then v. Now, if I looked at a fixed value of u, for example, for a fixed value of u, I'm going to have a what? If this is fixed and this is fixed, then I have a circle, basically in the xy component, whose length is just the sinh of u, right? And then that's what? And the last entry is v, so in other words, I get a helix. If I fix u, I'm going to get a helix. And so as I get one helix, and as I alter u, then what happens is I get more and more and more helices, so I'm gluing together a whole bunch of helices. So what's happening over here is I have a whole bunch of helices that are being glued together, right, on a surface, right? So in other words, it's a union. That's our helicoid. Beautiful. Of course, I'm not a very good artist, but that's the whole point. That's basically, if you can imagine like a propeller blade going, right? The propeller blade is going to swipe out a helicoid, essentially, right? Good. What's Ru? Ru is going to be just going to be cos u cosine v, cos u sine v, and then 0. What's Rv going to be? Rv is going to be a sin u negative sine v, a sin u cosine v, sin u cosine v, and then a 1. So what's my first fundamental form over here? My first fundamental form is going to be Ru dot Ru. That's going to be just a cos squared. So I have a cos squared u du squared. And then what's going to happen down over here? Down over here, we're going to have what are the cross terms? Well, this and this are equal and opposite to each other, so there's going to be no cross term over here. Then finally, I'm going to have a 1 plus sinh squared, 1 plus sinh squared of u dv. But of course, 1 plus sinh squared is cos squared, right? So this is exactly equal to what? This is exactly equal to just a cos squared of u, and then a du squared plus dv squared. So it's conformal, right? And of course, by the same reasoning, what do we see? By the same reasoning, we see that RUU plus RVV is going to be equal to 0. Now, how can we see that? Because if I do a u derivative, this is going to turn into sinh. If I do a v derivative, this is going to turn into cos. One's positive, one's negative. If I do a u derivative of this, it's going to be a sinh. If I do a v derivative, this is going to be negative sign, equal and opposite. So the Laplacian of this vector field is also equal to 0, right? And this implies that the helicoid is a minimal surface. So the helicoid is a minimal surface. So we have two examples of minimal surfaces. In fact, it's the only ruled one, right? It's the only ruled minimal surface. That just follows again from an OD, which we'll see in further videos, right? But of course, the other thing to consider over here, and it's an elementary observation, is that this helicoid's not compact either, right? Not compact. And we'll see in further videos that no minimal surface can be compact, because on a compact surface, there necessarily needs to be a point of positive Gaussian curvature, because at some point, if the surface is compact, the surface can be fit inside of the sphere, right? And so at that point of contact with the sphere, we know that the Gaussian curvature has to be at least the curvature of that sphere, of like the contact sphere, right? So basically, in some sense, it's like a osculating sphere, right? And so the curvature at that point has to be positive, but if the Gaussian curvature is positive, that means that the principal curvatures have to have the same sign. They have to be both positive or both negative. If they're both positive, you can't have k1 plus k2 being equal to 0. If they're both negative, you can't have k1 plus k2 being equal to 0. So there's no way that I can have a compact minimal surface, which you'll see in a further video. Thank you very much.